So last time we left off, we had just, so let's go look back at the results real quick before we jump in. Here we go. So we had looked at A1 here, so just a general algorithm to compute the Cayley configuration space of a 3D composable, 1DOF 3D composable graph over a base non-edge F. And that was just by realizing all extreme linkages. Because if you recall, the endpoints of our oriented or unoriented Cayley configuration space correspond to realizations of these extreme linkages, where triples of points corresponding to adjacent bars or implied bars, if you recall from recombination steps, are collinear. So that means that we get a change in forward orientation. So here, for example, V2, V4, and V7, V4, we've got a implied bar V2, V4, and a bar V7, V4. And in an extreme linkage, if this were to stretch out all the way, we would have V7, V4, V2 collinear. So that was A1. We hadn't discussed A2. That's actually what we were going to, we said we would assume, and we were going to show today. So we'll discuss it a bit today. And then we had discussed A3, which was to find, to show that there are at most two continuous motion paths between realizations and to show how to find these. And this was just, I believe this is where we left off last time. And this was basically just traveling along the intervals of an oriented Cayley configuration space and switching between orientations. So you hit an interval, you jump to a new interval in a different oriented Cayley configuration space. And the important part was that the orientation only changes by one entry. So by doing this, we can just jump along these intervals from either, if we're starting at a realization P in an interval, we can either go left or right to either endpoint, and those give us our two continuous motion paths. So that's where we left off. Today, we're going to look at C1 and C2 here. So we're going to show first how to give a characterizations of graphs with QRS complexity, and then to show that, pairs with QRS complexity, so G comma F. And then we're going to show that we don't really need to talk about the pairs. We just need to talk about the graph. So if G comma F has QRS complexity for one non-edge F, it has them for all non-edges F, such that G union F is tree decomposable. So that's what we're going to talk about today. And if we have time, we will look at this A2, this algorithm, because if you recall, there was, let me see, this theorem that we kind of just assumed. So this was about fixing the minimal orientation and looking at what the Cayley configuration space looked like. We said it was a single interval, and moreover, the length of any non-edge is going to be a continuous monotonic function of our base non-edge. So the monotonic was the new part. And in proving this theorem, we can come up with a faster algorithm. So we're not going to go through all the details, I don't think, but I can give you kind of an overview of it. Once you see the algorithm, the proof of this theorem is very easy. Okay, so let me know if you have any questions on what we covered last time. So now we're going to focus on these two results. So we want to characterize pairs G comma F with QRS complexity. All right. So we had the definition from last time that a pair G comma F has QRS complexity. First off, our original definition was it had QRS complexity if the realization corresponding to an endpoint in a Cayley configuration space can be solved via a tree decomposition. And then we said that that was equivalent to every extreme graph being tree decomposable. And that was because, as we said, a realization at an endpoint realizes an extreme linkage. Okay, so one algorithm we have is for every vertex, possibly every vertex corresponding to a recombination step, we're going to check if the extreme graphs are tree decomposable, which takes OV squared time for each graph by this paper here, Fudos and Hoffman, 1997. So overall, you do this for every extreme graph, and it will take cubic time in the number of vertices in the worst case. So we can do better, as the theorem before stated, which was we can do it in quadratic time for graphs with QRS complexity. So that's why we're interested in characterizing QRS complexity. Okay, so I'll go back to this definition in a moment, but I'll just kind of explain, what it means visually. So there's a partial order. So once you're given a pair G, so this is our graph G, and we're given this non-edge F here, this dash non-edge. Once you're given those two things, you've got a partial order on the recombination steps of G from F. Okay, so maybe I can zoom in real quick a little bit. So for example, you've got, it's a little blurry, but let me know if what I'm saying you can see visually. So you got V naught and you've got V prime naught. And for example, we've got this V2. And we get V2 by doing the recombination step with clusters T3 and T4. Likewise, V3 can be added to the graph with a recombination step on T5 and T6. But it doesn't matter the order we do these two things in. And also V1 and V4 also have clusters coming off of our base non-edge. So T1's here, and T2 kind of curves around this way. And same thing with V4 over here, T8, T7. So those four recombination steps, it doesn't matter what order we do them in. So what we're going to say is we're going to define these sets of vertices called levels. So level naught is going to just contain V naught and V prime naught. Level 1 is going to contain all vertices whose base pair is V naught, V prime naught. So 1, 2, 3, 4. Furthermore, it's going to contain all of the vertices in the clusters involved in these recombination steps. So it's going to, for example, V1 is in level 1, and so are all the vertices in T1 and T2. Okay, then level I, for I greater than 1, is going to contain the vertices whose base pair, maybe it may be easier to just see, let me try to, there we go. That's not what I want. Might be easier to see the definition in this case. Level I is the set of all vertices whose base pair is UW such that U is in level J and W is in level K, where they don't have to be distinct, but they can be, such that the maximum level of J and K is I minus 1. So it just means that your base pair comes from lower levels if you're in level I, and they can come from at most level I minus 1. Okay, and then a last level vertex is just going to be a vertex contained in the very last level of all your levels, right? So if we look here, like we said, we've got V1, V2, V3, and V4 in level 1. V5 and V6, their base pair are level 1 vertices, so they're going to be in level 2. V7 has level 3 vertices as its base pair, so it's level 4. Oh, sorry, is that, we've got 1, 2, oh, sorry, so level 3. And then V8 is in level 4, because it has a level 3 vertex, and it's got a level 1 vertex. So it's in level 4. Okay, so those are the levels of our graph. Hopefully that's clear. So now we're going to notice something. Well, we're just going to define a kind of a structural component of our graph. And it's going to involve 4 maximal clusters, and it's going to be called a 4 cycle. So a 4 cycle is a set of 4 maximal clusters such that each one shares exactly, each pair share exactly 1 vertex, and these 4 vertices that are shared are distinct. So for example, down here, if this picture is big enough, you've got T1, T2, T3, and T4 form a 4 cluster, with the shared vertices being V0, U1, V0 prime, and U2. Sorry, that's V2. Okay, the labeling's a little weird, but it's these 4 vertices. Okay, and then similarly, some of the ones that may be a little harder to see once you have a more complicated graph, T6, T5, T1, and T3 also form a 4 cluster. And then you've also got T5, T6, T7, and T8. Those also form a 4 cluster. And in this case, the shared vertices are U2, U2 not, or U2 prime, V3, and V4. Right? So now we can define some of the important pairs of vertices in these 4 clusters. Oh, and we're also going to say that 2 maximal clusters are adjacent in a 4 cluster if they share a vertex. So down here in this obvious 4 cluster, 1, 2, 3, 4, T2 and T3 are not adjacent because they don't share a vertex, but T2 and T4 are. Okay, and then some important pairs of vertices in these 4 cycles are going to be the diagonal pairs, which down here in this example of T1, T2, T3, and T4, our diagonal pairs are, we'll use the vertices not in parentheses. We've got V1 and V2 is a diagonal pair, and then V0 and V prime not is a diagonal pair. Okay, and then we're going to define one other type of pair of vertices that we're going to care about, and those are chordal pairs. So remember, within these maximal clusters, we can have vertices. These are just kind of an abstract visual of them. So a chordal pair is just going to be a pair of vertices coming from an adjacent pair of maximal clusters. So for example, over here on the right, this pair, U2, U2 prime, is a chordal pair in the clusters T6 and T4. Now, it doesn't just mean that they are a chord between adjacent pair of maximal clusters. They have to be adjacent clusters in a 4 cycle. So in this case, the 4 cycle where U2 and U2 prime is a chordal pair is T2, T4, T5, and T6. That forms our 4 cycle, and T4 and T6 are an adjacent pair in that 4 cycle. Okay, so we've got our levels, which tell us about kind of the partial order of these vertices, and then we've got our 4 cycles. So now we're going to give this characterization of graphs of pairs GF with QRS complexity in terms of these 4 cycles and these levels. So a pair G comma F with at least 6 maximal clusters, because otherwise it's kind of uninteresting, has QRS complexity if and only if for every recombination step where V sub k is in level 3 or higher, there's a 4 cycle such that its base pair U sub k and W sub k are contained in an adjacent pair of maximal clusters. Okay, so a visual of what this means. If we take V0 prime here, this kind of vertical pair, and we visualize the construction of this graph starting from this non-edge, we want to only really care about the vertices in level 3 or higher. So V1 is in level 1, V2 is in level 1, V3 is in level 2. Now we look at V4, that's in level 3. So we want to make sure that V4, its base pair, which is U2 and U2 prime, we want to make sure that they're contained in adjacent pair of clusters in a 4 cycle. So T5 and T6, T2 and T4 form a 4 cycle, and the base pair come from an adjacent pair of maximal clusters in this 4 cycle, T5 and T6. Okay, so that's going to be our characterization. So let me know if this statement isn't clear, because now we're going to go ahead and prove it. Okay, so one direction is kind of easy. So we're going to assume that our pair G comma F has QRS complexity. And we're going to consider a recombination step where VK is in level at least 3. Okay, so because our pair has QRS complexity, we know from the definition of that the extreme graphs are all tree decomposable. So it can be constructed from our construction step that we're interested in, the very last one, U sub k, W sub k, right? That was because the extreme graph is tree decomposable, it can be constructed from any of its edges, and in particular, the last reconstruction or the last recombination step that we're interested in. Okay. Now, also notice that since V sub k is in at least level 3, the graph that we get from performing the first k-1 recombination steps must have at least 4 maximal clusters. So you can see that from here, this graph right here. Ignore T1 and T3 because we don't need these. All this is saying is to get to V4, which is in a level 3 vertex, we have to have this construction step. So here I'm taking V1 and V2 to be my base non-edge. We have to have this construction step, T2 and T4, to get us a level 1 vertex, then T5 and T6 to get us a level 2 vertex, and finally one more to get us a level 3 vertex. So what this is saying is that in the graph, just by performing, in this case, we only need 3 construction steps to get here. So in the graph that we get by just performing the first 2 construction steps, we have 4 clusters, which is true here, right? And this isn't just an example. You can say this, abstractly. So we know that we have at least 4 maximal clusters to work with. Okay? So that means in order to construct our extreme graph, we have at least 2 recombination steps. Because what is an extreme graph? Just to make sure we all remember, an extreme graph here, the third extreme graph, would be instead of adding T7 and T8, we just add an edge between U2 and U prime 2. Okay, so we're saying that this is tree decomposable if we just add U2, U prime 2, and we can construct this extreme graph from this base pair. And since we know that the graph G sub f of k-1, so the one that just performs these 2 construction steps, has 4 maximal clusters, we know that in order to obtain this graph, the extreme graph, we have to perform the recombination step that adds T5 and T6 in this case, and then the one that adds T2 and T4. So we're going to have at least 2 recombination steps. Okay. And notice that the first 2 recombination steps that we perform forms a 4 cycle. So now this picture will be more useful, right? This is G sub f of k-1. And then we get our extreme graph by adding an edge between U sub k and W sub k here. And here are our 4 clusters that are contained in G sub f k-1. So we have to do 2 recombination steps that add these 4 clusters. So the very first one has to contain u sub k and w sub k, since we only have the edge u sub k, w sub k to begin with. So that's going to add T1 and T2. And then it's kind of obvious that the next one is going to create this 4 cycle, because we're going to build something off of T1 and T2. So our 4 cycle is going to be T1, T2, T3, and T4. And P3 and P4 in this case could be U sub k, W sub k, but it doesn't have to be. Either way, we get a 4 cycle. It doesn't matter whether they are the same or not. Okay, so we have this extreme edge. We have this 4 cycle, and that almost proves it, because now if these if these clusters are indeed maximal clusters of F, then when we do this last construction step, the base pair, U sub k and W sub k, are contained in an adjacent pair of clusters in a 4 cycle. Okay. And we know that they are maximal clusters of F, actually, because they're contained in G sub F of k minus 1. So therefore, this direction is done, right? All we had to do was we took a vertex that's in level 3 or higher. We showed that there's a sufficient number of maximal clusters in G sub F of k minus 1, meaning enough to perform 2 recombination steps, so 4 clusters. And we performed those 2 recombination steps. We got a 4 cycle, and that proves it, because now we've got U sub k and W sub k in an adjacent pair in a 4 cycle. So that's one direction. If our graph, or if our pair G comma F has QRS complexity, then this is true. The 2 conditions, or the 1 condition, V sub k is in a 4 cycle, its base pair is in a 4 cycle, and they're in an adjacent pair of clusters. So let me know if there's any questions about this direction. Okay. So sorry for the hand-drawn sketch here. There had to be a minor change. In particular, before it claimed that it needed to be level 2 or higher, but it actually needs to be level 3 or higher. So I had to redraw the base case. Okay. So for the other direction, we're going to assume that for every recombination step in our graph, where V sub k is in level 3 or higher, there is a 4 cycle such that the base pair of vertices are contained in an adjacent pair of maximal clusters. And we're going to show that G comma F then must have QRS complexity. And we're going to do this by induction on the number n of recombination steps. All right. So, and remember, our assumption is that G has at least 6 clusters, because otherwise it's uninteresting. So that's why the base case here is n equals 3. That'll give us these 6 clusters. And you can just easily verify by looking at the extreme graphs that this is going to have QRS complexity. So the first, the G hat naught extreme graph is just going to add an edge between V naught and V prime naught, and that's obviously tree decomposable, because K2 is tree decomposable in the base case. The next one, we're going to have this cluster and this cluster, and then here's our next base pair. We add an edge between them. That's tree decomposable because we can perform the recombination step that adds this cluster and this cluster. Okay, and so on and so forth. It's easy to see anything like this is going to be QRS complexity. All the extreme graphs are going to be tree decomposable. Okay, so that's the base case. Okay, let me see. Yeah, okay, so we've got this picture. Okay, so for the induction hypothesis, we're going to assume that G comma F has QRS complexity when we only perform k minus 1 recombination steps, and we're going to show it for k recombination steps. Okay, and by the inductive hypothesis, what it means to have QRS complexity is that all the extreme graphs for recombination steps less than k are tree decomposable. Okay. So we're going to consider this recombination step that adds v sub k. Oh, I see a chat. Yeah, Dr. Sithram saying that the point is that the cycles are of length less than or equal to 4, the 4 cycles. So we don't have to be careful about excluding lower levels.
It's not the point is that we don't want large cycles.
Yeah, right.
Yeah. So exactly 4 is not so relevant.
Yes, right.
Okay. Yeah.
Okay. Right. So we're going to consider this recombination step that adds the vertex v sub k, and it's got the base pair u sub k, w sub k. Okay, so by assumption, because we're doing the other direction now, there is a 4 cycle in our graph such that u sub k and w sub k are contained in an adjacent pair of maximal clusters. And without loss of generality, we're just going to say that they're contained in T1 and T2, and that T1 and T2 are an adjacent pair. Okay, so we have something that looks like this, where we've got g sub f of k minus 1. We've got our base nonage somewhere over here. And we've got this last recombination step and our 4 cycle of interest. Okay, so we're going to note something that's kind of obvious, but it's important, so we're going to show it real quick. During these recombination steps, it must be the case. So during these recombination steps, this 4 cycle is going to kind of come into existence in our graph, right? And it must be the case that for any recombination step that adds clusters to this 4 cycle, it must add exactly 2 clusters. So in particular, this 4 cycle is constructed using 2 recombination steps, right? Otherwise, if this isn't the case, then the only case to consider is 4 recombination steps that each add a single maximal cluster to this 4 cycle. So why don't we have to consider the other cases? Well, if you add it all at once, that's not a valid recombination step, just by the definition of tree decomposability. And if you add 3 at once, that's not a valid recombination step. So it could be the case that maybe all our recombination steps, like, it's T2 and some other cluster outside of the 4 cycle, T3 and then some other cluster outside of the 4 cycle. That's the only case that we're considering, that we continue doing that kind of recombination. Okay, well, we can add T1, T2, and T3 in this fashion, but then notice that when we add T4, T1, T2, and T3 were already in our graph. And so that means that T4 shares 2 vertices with our previous graph. But that's not a valid recombination step, because in a recombination step, the 2 clusters that are added must share exactly 1 vertex with the rest of the graph, and then 1 vertex with each other. Okay, so that's not allowed. So since that's a contradiction, we must add clusters 2 at a time to this 4 cycle. Okay, so now we're going to consider the recombination step that completes this 4 cycle. So it adds the last pair of adjacent maximal clusters. And without loss of generality, let that be the clusters T3 and T4, right? So T1 and T2 are already in our graph, and we're saying that this recombination step completes the 4 cycle by adding T3 and T4. Okay, so this recombination step is M is less than K. Okay, which means that by our inductive hypothesis, as we previously noted, the mth extreme graph is tree decomposable. So in particular, if we, instead of adding T3 and T4 and ignoring this T5 and T6, which isn't in our graph, we're in a state where we just have this T1 and T2. U sub m and W sub m in this case are P3 and P4. And we're saying that adding an edge between P3 and P4 yields a tree decomposable graph. Okay, so that means that this tree decomposable graph, this extreme graph, can be constructed from P3 and P4. And in particular, the very first recombination step that we perform when we just have this edge can be T1 and T2. Right, because that's going to be a level P1 right here is going to be in level 1. Its base pair is the edge, are the vertices that we start with. Okay. Moreover, once we've performed all the recombination steps to get this extreme graph, so the graph that has the edge P3, P4, and the first K-1 recombination steps. Sorry, M-1, because we're at step M. Once we've done that, we can remove this extreme edge, and that gives us, by definition, G sub F of M-1, because remember, to get the extreme graph, we take this graph and we add the extreme edge. So now we're just removing it to get this. And then, now we're just at some point in our construction of G from F, so we can continue the construction. So we can perform the mth to the K-1 recombination steps. And that will get us up to G sub F of K-1, so the graph that we see here, without T5 and T6. Okay, so this will be useful, that we can construct the rest of our graph once we have P3 and P4. That's basically what this is saying. At any point where we have P3 and P4, we can perform this process. We can just pretend like we've removed the edge of the extreme graph and then perform the construction steps to get G sub F of M-1, and then perform the rest of the construction steps to get G sub F of K-1. Okay, so finally, starting from our base pair that we're interested in, U sub K, W sub K, we're going to first perform the 2 recombination steps that add T1 and T2, and then T3 and T4. Okay, and we know that we can do this because U sub K and W sub K, by hypothesis, are contained in a 4 cycle, and they're contained in adjacent pairs of clusters in the 4 cycle. Okay, well, now the graph contains U sub M and W sub M, which were just P3 and P4. And now we just do exactly what we said. We can apply the construction that we just talked about. And the only catch here is that, remember previously, the extreme edge here was between P3 and P4, where instead of adding the clusters T3 and T4, we just added that extreme edge. So now we can perform the previous construction with these clusters added on, T3 and T4, but that doesn't prevent anything, because these are just kind of tacked on. Right, so now we can perform this construction where we take P3, P4, we construct the extreme graph, we delete the edge P3, P4, then we construct G sub F of K-1. We're going to do all that with just this T3 and T4 added on. Okay, and so that gets us to G sub F of K-1 union U sub K, W sub K, because we started with this edge. And that gives us the kth extreme graph. Okay, so what did we actually do? We performed 2 recombination steps from U sub K and W sub K, and then we kind of pretended that our base pair was P3 and P4 and performed the rest of the recombination steps that way. But that's the same as just saying that our base pair is actually U sub K and W sub K. So therefore, we've shown that this extreme graph is tree decomposable. And in particular, you just do T1, T2, then T3, T4, and then all the recombination steps from P3 and P4 to get G sub F of K-1. Okay, so that proves the other direction by induction. So any questions on this proof? I hope that was clear. It's it's a lot of just kind of dealing with these extreme graphs, visualizing what recombination steps you can do given the assumptions we have, right? Like we needed to ensure that we have this 4 cycle here, or that we can do the recombination steps to get this 4 cycle. Okay. So now we've proven this 4 cycle theorem. So now this kind of gives us a much better algorithm to check whether a graph, a pair G comma F has QRS complexity, instead of just checking every extreme graph, right? So the way to do that, and I won't go, it's kind of a wall of text, but I won't go over all the details. But the point is, the overall picture that you should just take away from this is that we're going to perform the recombination steps of our graph one at a time. So that just takes O of V time. And then after each recombination step, we're just gonna kind of do like almost, we're gonna do an amount of work that is also O of V. And that work is going to keep track of this set L. And what this set L is a set of adjacent pairs of clusters in 4 cycles. And all we have to do is ensure that at every recombination step, our base pair is taken from some pair in L. Since L is going to be our adjacent pair of clusters in 4 cycles, obviously our next base pair needs to come from L, or it needs to be contained in clusters in L. Otherwise, it's not contained in an adjacent pair of clusters in a 4 cycle, which would tell us by the previous theorem that it doesn't have QRS complexity. So that's all we're going to do. And you can do this very quickly. You can do it in O of V time. Okay, so that's just kind of a nice algorithm that we get from the 4 cycle theorem. Okay, and then the one other kind of combinatorial result we want to show is that if a pair G comma F has QRS complexity, then so does the pair G comma F prime for any non-edge F prime. You know, since this is a pair such that G union F prime is tree decomposable. Whenever we write it in this pair, we mean one DOF tree decomposable graph and a base non-edge. Okay, so what we're going to do is we're going to prove this by contradiction. Any base non-edge F dash, yes, right. So we're going to prove this by contradiction. We're going to assume that G is the graph with the minimum number of recombination steps that violates this claim. So the minimum number of recombination steps such that for one pair G comma F, such that one pair G comma F has QRS complexity, but another pair G comma F prime does not, where obviously these two are distinct. Then what we're going to do is we're going to show that we can actually, if this is the case, we can actually just leave out one of the final recombination steps. We're going to leave out a recombination step on a last level vertex. And this is going to give us another graph such that it has QRS complexity with F, but not QRS complexity with F prime. And that's going to be a contradiction because we performed one fewer recombination steps and obtained the same graph. So it contradicts the minimality assumption on G. Okay, so that's going to be the idea. So let's go through the details here. So we're going to let F be V1 and V2. And we're going to let, sorry, that should say F prime there. F prime be V prime 1, V prime 2. And they are pictured down here, right? So F is V1, V2, F prime is V prime 1, V prime 2, right there. Okay. And like we said, we're going to assume G is the graph with the minimum number of recombination steps, such that G comma F has QRS complexity, but G comma F prime does not. Okay, so the first thing we're going to observe is that f and f prime cannot be contained in the same adjacent pair of maximal clusters. Right, yes. So yeah, that's important to point out. The minimality statement that we're making, that G has the minimum number of recombination steps, it makes sense because if you recall, these recombinations have the Church-Rosser property, meaning that any set of recombinations will get us our graph G, and all sequences of recombinations have the same number of recombinations. So it makes sense to make this claim on minimality. And we can compare either the number from G comma F or G comma F prime of recombination steps. Okay. So the first observation we're going to make is that F and F dash cannot be contained in the same adjacent pair of maximal clusters, or even in the same 4-cycle, really. Otherwise, they would have the same algebraic complexity. Why? Because all of their extreme graphs would be the same, right? They'd basically be performing all the same recombination steps. So we'd be looking at all the same extreme graphs. And if those are tree decomposable, then both F and F dash have QRS complexity. If any one of them is not, then neither have QRS complexity. So as the picture down here shows, they must be in different 4 cycles, right? So hence, this means that G has at least 2 recombination steps from either non-edge, from either F or from F dash. So the picture down here shows G with the first 2 recombination steps from F and the first 2 recombination steps from F dash. Okay. So all we've shown here is that if we assume to the contrary, all this stuff, that G comma F has QRS complexity, but G comma F prime does not, then we must be in this situation pictured below. Okay. So now this 4-cycle, there's a base pair for, let's consider the one at the bottom right. So we're dealing with F. We have added T1 and T2. The next recombination step adds T3 and T4. And the base pair is in T1 and T2. It's W1 and W2. So we're just going to call this G, W1 comma W2. Likewise, we're going to call W prime 1 and W prime 2 G prime. Okay, so from what we just said, since F and G, and respectively F prime and G prime, are contained in the same adjacent pair of maximal clusters, then G comma F and G comma G must have the same algebraic, must have the same algebraic complexity, right? Because all of their extreme graphs are going to be the same. Okay, and likewise, G comma F dash and G prime, or G comma G dash, are going to have the same algebraic complexity. Therefore, without loss of generality, we can just kind of perform this argument assuming F is equal to G and F dash is equal to G dash. Okay. Now, here is a kind of an important property that's going to be true if everything we've assumed so far is true. So if V is a last level vertex, so it's one of the last ones added, and nothing kind of depends on the vertex V. The vertex V has clusters T1 and T2 when it's added, and nothing is built off of T1 and T2. Okay, so that means that V is a last level vertex. So if V is a last level vertex in the construction of G from F, then V must be a vertex of F dash. So what we're saying is if we start over here with F and we perform all of our construction, our recombination steps, one of the last level vertices, or all of them actually, must be a vertex of F dash. Okay. So suppose, and we're going to show this, we'll prove this now. So suppose that V sub m is a last level vertex, and its base pair is U sub m, W sub m. And suppose that it's not a vertex of f dash. Okay, so since U sub m and W sub m is a non-edge, because all base pairs are non-edges, the two unique maximal clusters of f containing V sub m form a 1DOF tree decomposable graph. So what does this mean? It means that the maximal cluster containing U sub m and the maximal cluster containing W sub m form a 1DOF tree decomposable graph. So sorry, if we look here, let's just consider U2. All this is saying is that if I just take the graph T3, T4, then it's 1DOF tree decomposable. Because if we add the edge W1, W2, then we get a tree decomposable graph. Okay. So since it's 1DOF tree decomposable, it must, these clusters must also be maximal clusters of f dash, right? So the clusters involved in this construction step are maximal clusters of f, and they are also maximal clusters of f dash. Hence, we can perform this recombination step last in the construction of G from f dash, right? Because in any construction, V sub m is going to be a last level vertex, and we're just saying that we're going to consider the two maximal clusters that are involved in this recombination step, and we're going to do that recombination step last when we're building G from f dash. Okay, so what does that mean? Well, that means that if we consider the graph before this last recombination step, they must be the same by the Church-Rosser property. So G sub f, building G from f and performing the first k-1 recombination steps gives us the same graph as building G from f dash and performing the first k-1 recombination steps. Okay. Also, by assumption, the kth extreme graph, since G comma f has QRS complexity, the kth extreme graph is tree decomposable. But the kth extreme graph for f dash must then be tree decomposable because these are the same extreme graphs. Now we know that G comma f dash does not have QRS complexity, which means some extreme graph is not tree decomposable. But this implies that some other extreme graph, extreme graph of less than k-1 recombination steps is not tree decomposable. Okay, well, what does this mean? This means that we can just consider all the recombination steps up to that point where we reach the first extreme graph that is not tree decomposable. And that graph, G dash, has QRS complexity on f, but not on f prime. So that contradicts the minimality of G. Okay. And so we're just going to get through this proof, I think, because I think I'm almost out of time. So now we know that our last level vertex has to be if we build the graph from f, our last level vertex has to be a vertex of f dash. Okay. So let V be a last level vertex in the construction of G from f. By our previous claim, V is either W1 dash or W2 dash, because we remember we said without loss of generality, we can just let f dash be this non-edge instead. So V is either W1 dash or W2 dash. So without loss of generality, let it be W1 dash. Okay. So, sorry, where is U? Should that say V? Oh, no, okay, we got this. Okay, so f dash, note that f dash, which is W1 dash, W2 dash, and f dash dash, which we're going to say is this non-edge, u1 dash, u2 dash, have the same algebraic complexity because they're contained in the same 4 cycle. Okay, so starting from f dash dash, which is this one, u dash 1, u dash 2, we can perform the recombination step that adds t1 dash and t3 dash, which gives us w dash 1. And then we can perform the recombination step that adds t4 and t2, which gives us w dash 2. And then the construction of g from f dash, which is this one, is the same as the construction from f dash dash. So basically, once I create this 4 cycle, the construction from either this non-edge or this non-edge is going to be the same. Okay, so since V is a last level vertex, we can just not perform W1 dash because remember V equals W1 dash. We can not add W1 dash to our graph. Okay, but since we said that this non-edge and this non-edge have the same algebraic complexity, then by not adding this vertex, we get a smaller graph, fewer recombination steps, such that this non-edge does not have QRS complexity, but F does. And that contradicts the minimality of G. So that shows that they both must have the same QRS complexity. Okay, I'm not going to be able to get to the other stuff since I think I'm already over time. But the basic flavor here is that once we have the 4 cycle theorem, we can prove some really nice things about this subclass of 1DOF tree decomposable graphs that only have one last level vertex. We can come up with a fast algorithm to compute Cayley configuration spaces of these graphs that only have one last level vertex. And then we can put all that together to get the Cayley configuration space of any 1DOF tree decomposable graph that has QRS complexity. So that's kind of where we would have gone if we had had more time. So sorry if this proof was a little hairy. There's a lot of kind of non-edges and vertices to keep track of. But if you have any questions, just let me know, or I can go over it anytime. So thanks.
Are there any questions? So I have a question. You had some statement there about V cubed early on, when we were talking about the QIM algorithm. What was that? Oh, this is for characterizing. Yeah. Yeah, but this is sort of like the least interesting application of the 4 cycle theorem, though.
William, you're muted.
Yeah, I didn't realize. Okay, so no, I was just saying that this is to characterize graphs with QRS complexity by just checking all of their extreme graphs to see if they're tree decomposable. But yeah, this was just kind of an observation that we could do it just with the definition of all extreme graphs being tree decomposable. But obviously we can do it much better. And yeah, this isn't the biggest use of the 4 cycle theorem. It was just to kind of build up to it.
Right. So one question would be, what are the good uses of the 4-cycle theorem?
Yeah, so, well, one would be the stuff that I wasn't able to get to. So there is, we were going to discuss this, which was an algorithm to compute the Cayley configuration space for QRS complexity, or for pairs with QRS complexity in quadratic time and the number of vertices. And
As
this,
opposed to the ELR algorithm.
yeah, as opposed to the ELR algorithm, which could take exponential time.
Yeah.
So the kind of nice use of the 4-cycle theorem is this lemma right here, for special types of graphs called one-path graphs, where a one-path graph is just a graph where if you construct it from F, it has exactly one last level vertex. So kind of just like easy graphs to construct. And the point is we can, using the 4-cycle theorem, say exactly where all of the base pairs of vertices are going to be as you construct, as you perform each recombination step. And by doing that, we can then just kind of relate distances of these 4 cycles. So we can talk about the distance of one diagonal pair relative to the other diagonal pair. And we can use this to compute the Cayley configuration space for these one-path graphs. And then it's just a simple observation that a non-one-path graph is just the union of one-path graphs, subgraphs. So that's kind of the more interesting application of the 4-cycle theorem. Yeah.
Yeah. And I think you use it also for the characterization of low QRS, QRS complexity as depending only on G.
Yes, we do. Yeah, it's used here because we're using the fact that these recombination steps, their base pairs have to be in adjacent pairs of clusters in 4 cycles. Yeah.
Yeah, so it's probably the key thing that's used for all of these properties of QRS complexity graphs.
Yeah.
Right? Yeah.
It's like the most powerful, I guess, kind of tool for these kinds of graphs.